Hi, please enjoy our Lab 4 presentation on monitoring air quality. This was presented by Matthew Perrin, Evan Huckins, Ashley McKibben, and Jordan Pack.
The COVID pandemic started in 2020 and ever since it has plagued the world. The COVID virus travels through aerosols, so people have been wearing masks to slow the spread because the virus is so big that it can't travel through a mask. One of the ways to help slow the spread is to monitor the air quality of rooms to see the concentration of CO2. And the amount of CO2 in the room can show how well the air is being ventilated. If there's the concentration of CO2 is really high, then that means the air is not being ventilated well. Steps can be taken to lower the concentration by opening a window, lowering the amount of people in the room, simple things like that. Our group was tasked with monitoring air quality in buildings on MSU's campus. We had the choice of doing whatever building we chose. The tests were done using a CO2 monitor. The one we used was called IAQ Max CO2. We compiled 4 tests. We did 2 for 2 hours and 2 for 24 hours. We figured the 2-hour ones would be done in a short period of time to see, like a classroom during a class, what the average CO2 would be during a 50-minute lecture, an hour, 20-minute lecture, and what it would be before people came in, after people came in, and when people were in class. And then for the 24-hour, we did 2 24-hour ones to see how it would be throughout the whole day. The data was then compiled on Gas Lab 2.1, where we would use the monitor, hook it up to my computer, transfer it over to Gas Lab, make a graph, chart the data, and then we would move that all over into Excel. The first 2-hour test of the 2 conducted was done in the Com Arts building, and it was done during a quiz and after a quiz. Everybody had masks on, and then it was left for, I believe, 20 or so minutes after the quiz ended to see what the CO2 concentration would be once people left. The second 2-hour test was done in Bessie room 304. It was done during a IH class with around 40 to 45 people all wearing masks. Not everyone had their masks over their nose. It was placed in the room about 30 minutes before class, and then was taken out once class finished. Roughly 2 hours. The CO2 concentration in the room might be higher due to people not wearing masks the proper way. The first 24-hour test was done in a dorm room on the 2nd floor in Owen Hall. The room was a single. I gave it to my friend who is an RA there. So I went to his dorm room, set it up next to his bed, right next to the window and the heater for about 24 hours, came back the next day, got it. No mask was worn in the room, probably around 1 or 2 people for the most part of the day. And so that's what we did for the first 24-hour test. And then the second 24-hour test was done in a kitchen at Owen Hall, how they have the kitchens for the students to go in and cook for themselves. It was placed next to a fridge that was left for 24 hours. So throughout the day, various people could come cook. They could open the fridge, close the fridge. Masks do not have to be worn in that area, so that can cause CO2 concentration to go up. That's how the second 24-hour test was done.
The data collected from the test was used to analyze the ventilation conditions at different locations. First, the carbon dioxide decay rate was determined for each location. This was done by plotting equation 1 as is shown versus the time after the maximum concentration occurred. The decay rate demonstrates the rate at which carbon dioxide is being removed from the location. This can be used as an indicator of the risk of transmission of COVID-19 or other similar airborne diseases. The maximum carbon dioxide concentration after the location had been vacated represented C, or concentration max, as well as the starting time, T equals 0. The outside air was sampled, and it was found that C outside, the ambient carbon dioxide concentration, was equal to 450 parts per million. After completing the calculations for equation 1 and determining those values, the plots were created as is seen in the example decay rate plot at the bottom of this slide. In these plots, equation 1 can be seen on the y-axis, and the time after the maximum concentration occurred is seen on the x-axis. The linear regression equation for each plot of data was determined. That's represented here by y equals mx plus b, and the decay rate at each location was taken to be the slope of the linear regression equation, or as seen on screen, m. After determining the decay rates, the rebreathed fraction over the duration of decay was determined using equation 2, or Rudnick and Milton's equation. The fraction of rebreathed air is essentially the fraction of air which is exhaled breath from any individual within the volume of the room. This parameter can be used similarly to the decay rate to analyze the ventilation further within a location. CO, the outside concentration, remained the same at 450 parts per million, and Ca, the concentration of carbon dioxide in the exhaled air, was estimated to be 38,000 parts per million. This Ca value assumes the individuals in the location are at a low level of physical activity. The rebreathed fraction was then calculated using equation 2, and the concentrations of carbon dioxide at each time step.
In order to further analyze the data, we created a mass balance model using the NIST tool. We modeled this after our first 2-hour test, which was conducted in a classroom in the CalArts building before and after a quiz. When using the NIST tool, it allows you to select a predefined model type. We decided to choose the lecture classroom model and kept all the parameters consistent with what the program had output, except we decided to change the number of the people in the classroom to more accurately model what that would have looked like. We estimated that there was a total of 29 people in the room during the quiz, 14 females aged 18 through 29, 14 males aged 18 through 29, and then a male professor aged 30 to 59. The weight of all these people was also based on an average weight for people in these specific gender and age groups. As you can see on this slide, the graphical output from the program is shown, as well as some of the program input factors, including ventilation per person, as well as the initial indoor and outdoor CO2 concentrations, which are at 0. You can also see the ceiling height set at 3 meters and a time metric, which we tried to keep consistent with our first 2-hour test. Looking at the graph on the bottom of the slide here, we can see the x-axis shows time since students entered the room. The blue line represents the buildup of CO2 at a lower ventilation rate, and the red line represents the CO2 buildup at a higher ventilation rate. From this, we can see that the longer the students are in the room, the higher the CO2 concentrations are going to be. And the graph also shows that the accumulation of CO2 is lower when there's a higher ventilation rate in the room. On this slide, you can see the results from our first 2-hour test, which was conducted during and after a quiz in the CalArts building. Time 0 on the x-axis shows the time since the maximum CO2 concentration was present in the room, and then from there we see the decomposition of carbon dioxide over time. At the end of the quiz, CO2 concentrations were at their highest, and after that, when people left the room, the CO2 decayed at a rate of 1.3753 inverse hours, which is represented by the equation for the line of best fit.
The second 2-hour test was conducted in room 304 of Ernst Bessie Hall. At time 0, the concentration was at its maximum right after the room had emptied. A maximum value of around 1,492 parts per million was observed. This value falls within the OK air quality level, and throughout the sampling duration remained at this level, which suggests moderately poor ventilation and moderate COVID-19 transmission risk. As seen in the graph, following the emptying of the room, the decay of carbon dioxide can be observed. As time passes, more carbon dioxide is being exchanged out of the room, either via intentional or unintentional ventilation. The decay of carbon dioxide in this location seemed to occur at a fairly constant rate. This is to be expected as the classroom was totally emptied, whereas in the 24-hour tests, the location could not always be confirmed to be totally empty. From the linear regression equation, the decay rate was found to be 0.7276 inverse hours.
On this slide, you can see the results from our first 24-hour test, which was conducted in a single dorm room on the 2nd floor of Owen Hall. You can see by looking at this, the graph doesn't quite look like the other ones, as the linear line of best fit is both negative and decreasing. Because of all the peaks and valleys in this graph, we concluded that the overall 24-hour decay rate is inconclusive. A couple of reasons for this could be attributed to the fact that the tenant was entering and leaving the room at different times throughout the day. It's also possible that they were having guests in the room, which would increase CO2 levels at those certain times. It's also possible that a window or door could have been open at some point during the day, which would allow for more ventilation in the room and would result in an increase in the decay rate. In the case of this specific 24-hour graph, it would make more sense to break it up into smaller sections and determine decay rates from those rather than looking at the overall 24-hour data?
The second 24-hour test was conducted in the student kitchen within Owens Hall. The maximum concentration within this dataset occurred at the beginning of the 24-hour period with 1,740 parts per million. This concentration is considered poor air quality and is suggestive that there may be high risk of COVID-19 transmission. Over the 24 hours following the maximum, the concentration overall trended downward, or rather decreasing carbon dioxide concentrations. Within an hour, carbon dioxide concentrations had fallen to a value within the OK air quality level, this suggesting less but not optimal COVID-19 transmission risk. The air quality remained within the OK air quality level throughout the rest of the test period. Within this plot, many spikes and dips in concentration can be seen. It's thought that this may be due to the locations, as it was not always confirmed to be totally empty. Additionally, the device was placed in a kitchen, which could have sporadic spikes in carbon dioxide concentrations due to cooking food. From the linear regression equation, the decay rate was determined to be 0.0172 inverse hours. Due to the sporadic changes in concentration and the long time duration, a lesser decay rate would be expected here, as is seen from the linear regression equation provided.
This slide looks at the rebreathed fraction, which deals with how much air we rebreathe that has been previously in other people's lungs. This graph was modeled after our first 2-hour test in the ComArts building, and we can see that the more carbon dioxide is in the room on average, the greater the rebreathed fraction percent will be. With this, a direct relationship is shown between the two. Generally, we want to keep this fraction as low as possible, as the less we are breathing other people's emitted air, the more likely we are to stay healthy and not catch airborne diseases in particular. From all this data, we can see that carbon dioxide decays slowly over time after people have left a room. With better ventilation, we will have a faster decay rate and therefore less risk for airborne disease transmission. Similarly, the rebreathed fraction of air decreases slowly over time within occupancy as well. Better ventilation means a greater decay rate, which reduces the rebreathed fraction more rapidly, reducing transmission risks. The longer a room is occupied and the more people are in that room, the more CO2 will increase, demonstrating an increased risk of transmission. Overall, the air quality in rooms before they were emptied typically fell within poor to okay air levels, and after the rooms were emptied, the air quality would improve to good air quality levels.
For each test done, the decay rate can be seen as steep in the beginning, and then as time goes on, it tends to even out. This is slightly interrupted when the test sites were used often, where spikes in levels can be seen on the graphs. Spaces with more human activity have higher levels of carbon dioxide, regardless of size ratio, as the dorm room tested has significantly lower levels in the low hundreds ppm than the lab tested, which was in the 1 to 2,000 ppm range. This shows that the dorm rooms have better ventilation than other spaces, such as classrooms and labs, and also shows that focus should be put on the areas of highest use on campus. These levels indicate a need for better ventilation systems in high-use areas, as well as a possible reduction in class size. Precautions need to be taken to lower these levels in order to decrease likelihood of spreading COVID-19 and other respiratory diseases. Some recommendations for decreasing carbon dioxide levels while continuing in-person classes include placing the most populated classes in larger rooms that are more open and have more doors and windows with access to the outdoors. This would help to circulate the air in the classroom and keep rebreathed air concentrations low. Smaller class sizes should also be implemented, and more sections of each class should be created so that classrooms are not as concentrated. More ventilation systems should be included in closed-off rooms, such as labs, that do not have access to windows. These class sizes should also be reduced, or more flexible hours should be implemented for these classes to reduce traffic of students. More time should be given in between classes as well to allow time for the decay of carbon dioxide in the classrooms used. One last but fun recommendation would be to hold classes outdoors when possible. This is less realistic for a school in Michigan compared to a school where it's warmer, but there's a bit of time each semester where weather would permit an outdoor class session, and students may enjoy a change of scenery as well. The implementation of one or multiple strategies in order to increase ventilation on campus is needed in order to slow the spread of respiratory illnesses.